Hello and welcome to Chapter 5, our discussion of Chapter 5 in the Fundamentals of Database Systems. Chapter 5 centers on the concepts of relational data model and relational database constraints. A relational model concept is an important thing to understand. The relational model of data is based upon the concept of a relation, hence the name relational model concept. The strength of the relational approach to data management comes from the formal foundation provided in the theory of relations. We review the essentials of the formal relational model in this chapter. In practice, there is a standard model based on SQL. This is described in chapter 6 and 7. We'll be covering those shortly as a language. Note there are several important differences between formal and practical model, and we'll see those here in a little bit. Continuing our discussion of the relational model concepts, a relation is a mathematical concept based on the idea of sets. So most of database theory comes from the concepts of set theory. So it's something that fit very nicely. The model was first proposed by Codd of IBM Research in 1970 in the following paper, a relational model of large shared data banks in the Communications of ACM in 1970. The above paper caused a major revolution in the field of database management and earned Dr. Codd the coveted ACM Turing Award. Informal definitions. Informally, a relationship looks like a table of values. A relation typically contains a set of rows. The data elements in each row represent certain facts that correspond to real-world entities or relationships. In the formal model, rows are called tuples. So when we talk about them in this context, rows become tuples. Each column has a column heading or header that gives an indication of the meaning of the data items in that column. In the formal model, these column headers or header is called an attribute name or just attribute. Here's an example of a relation in figure 5.1, the attributes and tuples of a student, a student. And you can see the tuples and the attributes. Informal definitions continued. The key of a relation is each row has a value of data items or set of items that uniquely identify that row in the table. This is called a key. If the student table SSN is the key, sometimes row IDs are sequential numbers that are assigned as keys are needed to be inserted into the record to make sure that they're done. These are called an artificial or surrogate key. They're columns or attributes that are basically added for that very purpose, just to uniquely identify each row. Alternative to that is the concept of a natural key, which is something that just naturally defines the uniqueness of something. The schema or description of a relationship is denoted by R and then of A sub 1 through N. R is the name of the relation. The attributes of the relations are the attributes A1 through N. For example, customer, cust ID, cust name, address, phone number. Customer is the relationship name. It is defined over the four attributes of customer ID, customer name, address, and phone number. Each attribute has a domain or a set of valid values. For example, the domain of customer ID is a 6-digit number. A tuple is an ordered set of values enclosed in angular brackets. Each value is derived from an appropriate domain. A row in the customer relation is a 4-tuple and would be consisting of 4 values. This is called a 4-tuple as it has 4 values. A tuple, which is a row, in the customer relation. A relation is a set of such tuples, rows. A domain is a logical definition, has a logical definition. For example, USA phone numbers are a set of 10-digit phone numbers that are valid in the United States. A domain also has a data type and is of particular or may have a particular format that's defined for it. US phone numbers may have the format of area code, exchange, and then the 4 digits, the last 4 digits. Where each of the Ds is a decimal number from 0 to 9. The dates have various formats such as year, month, day, and they may be of the form year, 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 dash, month, month, dash, DD. or month, year, and so on. Attribute name designates the role played by a domain in a relationship, used to interpret the meaning of the data elements corresponding to that attribute. For example, the domain date may be used to define two attributes named invoice date and payment date with different meanings. The relationship state is a subset of the Cartesian product of the domains of its attributes. Each domain contains the set of all possible values that the attribute can take on. For example, attribute custName is defined over the domain of character strings of a maximum length of 25. So the domain of custName is varchar 225. The role of these strings plays in the customer relation is that of the name of a customer. Formal definitions, a summary. So formally given a relationship made up of attributes A1 to N, the relationship R is a part of the domain of A sub 1 and would cross product with domain of A sub 2 and so on. R sub A1 through N is the schema of the relation. R is the name of the relation. A1 through N are the attributes of the relation. R sub big R is a specific state or value or population or potential instance of a relation. R thus is a set of tuples, rows. So R sub R is made up of the set of tuples T sub 1 through T sub N, and this is an N tuple. T sub I is basically the set of V1s through Vn's, where each V sub j element of domain A sub j, capital A. So let R sub A1 sub and A2 be a relation schema. Let domain of A1 and A2 be 0, 1. Let the domain of A2 be A, B, and C. Then the domain of A1 times domain of A2 is all possible combinations of those sets. So it's 0A, 0B, 0C, 1A, 1B, 1C, and so on. The relationship state is made up of what they are at that moment in time. So R sub R is a subset of that Cartesian product, so it has to be a valid set of states. For example, R sub R could be 0A, 0B, 1C. This is one possible state, population, or extension of the relation R defined over A1 through A2 and A2. It has three tuples, 0A, 0B, 1C. Definition summary, informal and formal terms. So informally it's a table, formally it's a relation, column header, and attribute. All possible column values is the domain. The row is a tuple, and the table definition is the schema of a relation, and the population table is the state of the relation. An example, figure 5.1, circling back to it, we have a relation name student with tuples, which are essentially the rows, and then the attributes, which are essentially the columns. Ordering of tuples in a relation R sub big R, tuples are not considered to be ordered even though they appear to be in a tabular form. This is an important concept to understand, is there's nothing that guarantees the order of a relationship other than if something is used to enforce it. Ordering of attributes in a relationship R and of values within each tuple. So we will consider the attributes in R sub A1 through N and the values in T sub or T from V1 to Vn to be ordered. However, a more general alternative definition of the relation does not require this ordering. It includes both the name and the value of each of the attributes. So in this case, the example is name is John, social security number is 1, 2, 3, 4, 5, 6, 7, 8, 9. This represents called a self-describing. The same state as previous figure, but with a different order of tuples, and this is considered to be valid. So you cannot necessarily assume the ordering of columns. It's not a great idea. Characteristics of relations, values in tuples. All values are considered atomic, indivisible. Each value in a tuple must be from the domain of the attribute for that column. If tuple T sub V1 through Vn is a tuple row, in the relation state R, which of R sub A, capital A1 through N, then each V1 or VI must be value in the domain from of A sub 1 or A sub I. A special null value is used to represent that an unknown or not available or inapplicable or not present value is in the tuple. Characteristics of relationships, on the continuing that discussion, we refer to component values of a tuple T by T sub A sub I or T dot AI. This is the value VI of attribute AI for tuple T. Similarly, T sub AU through AVW refers to the subtuple of T containing the value attributes A, U, V, and W, respectively in T. Constraints. Constraints determine which values are permissible and which are not. In the database, they are of three types: inherent or implicit constraints. These are based on the data model itself. Example, relational model does not allow a list of values of any attribute. Schema-based or explicit constraints, these are expressed in schema using the facilities ordered by the model. For example, max cardinality ratio constraints in the ER model. Application-based or semantic constraints, these are beyond the expressive power of the model and must be specified by enforcing the application program. When we talk about relational integrity constraints, these are constraints that are essentially conditions that must hold and be true for all valid relational states. There are three main types of explicit schema-based constraints that can be expressed in the relational model: key constraints, entity integrity constraints, referential integrity constraints. Another schema-based constraint is the domain constraint. Every value in the tuple must be from the domain of its attribute, or it could be null if allowed for that attribute. Moving on to additional discussion of key constraints. A superkey of R is a set of attributes SK of R with the following condition: no two tuples in any valid relational state R sub big R will have the same value for SK. That is, for any distinct tuple T sub 1, T sub 2 in R sub R, T sub 1 of S sub K cannot be equal to T sub 2 sub S sub K. This condition must hold in any valid state. Key of R, a minimal superkey, that is, a key is a superkey such that removal of any attribute from K results in a set of attributes that is not a superkey, does not possess the superkey unique property. A key is a superkey, but not vice versa. Examples, consider the car relational schema: car, state, registration number, serial number, make, model, and year. Car has two keys. Key 1 is state and registration. Key 2 is serial number. Both are also superkeys of car. Serial number and make is a superkey, but not a key. In general, any key is a superkey, but not vice versa. A set of attributes that includes a key is a superkey. A minimal superkey is also a key. If a relation has several candidate keys, one is chosen arbitrarily to be the primary key. The primary key attribute is underlined. For example, consider the car relational schema. Car has the possibility of using a serial number as its key. So if we underline it, then it becomes the serial number is the primary key. The primary key value is used to uniquely identify each tuple in a relation. It also provides the tuple identity. Also used to reference the tuple from another tuple. General rule: choose a primary key that is the smallest of the candidate keys in terms of size. Not always applicable. Choice is sometimes subjective, and it's something that may be that better defines the thing in a unique way. The car table with two candidate keys, license number is chosen as the primary key. And you can see that it is underlined to indicate that it is now the primary key. Relational database schema. The relational database schema is a set of S of R relation schemas that belongs to the same database. S is the name of the whole database schema. So the basic idea here is S is equal to the set of R sub 1 through N and the set of IC, which is the integrity constraints. Are the R1 through Rn are the common names of the individual relation schemas within the database S. Following slide shows a company database schema with 6 relation schemas, and you can see them on the screen. A relational database state, DB, of S is a set of relation states, dB equals the set of R1 through M, such that each R sub I in state of R sub I, capital R, and such that the R sub I relation state satisfies the integrity constraint specified in IC. A relational database state is sometimes called a relational database snapshot or instance. We will not use the term instance since it also applies to single tuples. A database state that does not meet the constraints is in an invalid state. Populated database state. Each relation will have many tuples in its current state. The relational database state is a union of all individual relational states. Whenever the database is changed, a new state arises. Basic operations for changing the database: insert is when you add a new tuple to the relation. Delete is when you remove one, and modify is you change an existing tuple. Next slide, figure 5.6, shows an example of state from the company database schema shown in figures 5.5 coming up. Population database state is on the screen, and you can see a given potential state of a database, and this is a relatively small database first, so that it's easier to understand. Entity integrity. The primary key attributes PK for each relation schema R in S cannot have null values in any tuple of R sub R. This is because primary key values are used to identify the individual tuples for any tuple T in the set of R. If the primary key has several attributes, null is not allowed in any of these attributes. Note, other attributes of R may be constrained to disallow null values even though they are not members of the primary key. Referential integrity, a constraint involving two relations. The previous constraints involve a single relation used to specify a relationship among tuples in two relations, the referencing relation and the referenced relation. Tuples in the referencing relation R sub 1 have attributes foreign key called foreign key attributes, so FK, that reference the primary key attributes PK, the primary key, of the referenced relation R sub 2. A tuple T1 in R1 is said to reference a tuple T2 in R2 if a T sub 1 of the foreign key is equal to T2 of the primary key. A referential integrity constraint can be displayed in a relational database schema as a directed arc from R1.fk to R2.pk. Referential integrity or foreign key constraints is the state of the constraints. The value of the foreign key columns or column, foreign key or FK of the referencing relation R1 can either be 1, a value of an existing primary key value of a corresponding primary key PK in the referenced relation R2, or it can be null. In case 2, the foreign key is R1 should not be a part of its own primary key because it loses its identifiability. Displaying a relational database schema and its constraints. Each relational schema can be displayed as a row of attribute names. The name of the relation is written above the attribute names. The primary key attribute or attributes will be underlined. A foreign key referential integrity constraints is displayed as a directed arrow from the foreign key attributes to the reference table. It also points the primary key of the referenced relation for clarity. The next slide shows the company relational schema diagram with referential integrity constraints added. You can see the arrows pointing the direction to indicate the primary and foreign keys and the referential constraints. There are other types of constraints. A semantic integrity constraint is based upon application semantics and cannot be expressed by the model per se. An example is the maximum number of hours an employee for a project he or she works on is 56 hours a week. A constraint specification language may have to be used to express these. SQL 99 allows create trigger, create assertion to express some of these semantic constraints. Keys, permissibility of null values, candidate keys, uniqueness in SQL, foreign keys, referential integrity, etc. are expressed by the create table statement in SQL. Update or operations on relations. Insert is you add a tuple, delete, you delete the tuple, modify to change it. Integrity constraints cannot be violated by the update operation. Several update operations may have to be grouped together. Updates may propagate to cause their other updates automatically. This may be necessary to maintain integrity constraints. For example, if you delete something that's being referenced, it's kind of a problem. So you'll need to do some stuff first. Unique update operations on relations. In the case of integrity violation, several actions may be taken. Cancel the operation that causes the violation. Reject the operation. So basically stop what you're trying to do. Perform the operation, but inform the user of the violation. Trigger additional updates so that the violation is corrected. This is a cascading update. And maybe a set null, or execute a user specified error correction routine to address the situation if it were to occur. Possible violations for each operation. Insert may violate any of the following constraints. Domain constraint if one of the attribute values provided for the new tuple is not of the specified attribute domain. Key constraints if the value of a key attribute in the new tuple already exists in another tuple in the relation. Referential integrity if a foreign key value in the new tuple references a primary key value that does not exist in the referenced relation. And entity integrity if the primary key value is null in the new tuple. Delete may violate only referential integrity if the primary key value of the tuple being deleted is referenced from another tuple in the database. Can be remedied by several actions. Restrict, cascade, set null. Chapter 6 will talk more about it. Restrict option rejects the deletion. Cascade option propagates the new primary key value into the foreign key of the referenced tuple or referencing tuple. And then set null option sets the foreign key of the referencing tuple to null. One of the above options must be specified during database design for each foreign key constraint. Possible violations for each operation. Now discussing update may violate domain constraint and not null constraint on an attribute being modified. Any of the other constraints may also be violated depending upon the attribute being updated. Updating the primary key, similar to a delete followed by an insert. You need to be specific. Similar options to delete. Updating a foreign key may violate referential integrity. Updating an ordinary attribute, neither primary or foreign key, can only violate the domain constraints. In summary, we've talked about the relational model concepts. We went over the definition. We talked about the characteristics of relations. We've discussed the relational model constraints and a relational database schema. Domain constraints, key constraints, entity integrity, and referential integrity. And then we also talked a bit about the relational update operations and dealing with constraint violations. As always, if you have any questions about the material I've discussed, feel free to reach out to me. That's what I'm here for. Stay safe, and we'll talk again soon.